Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're the kind of person who finds comfort in falling asleep to the quiet mysteries of the cosmos, rather than counting sheep or staring at the ceiling. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind ease into the darkness, your breathing slow, and your body grow light as the day's weight lifts away. Tonight, we're exploring something that feels almost impossibly lonely, yet strangely beautiful. We're going to drift alongside worlds that wander through the vast emptiness between the stars. Planets without suns, worlds that orbit nothing, bound to no star, no system, no cosmic family. They travel alone through the cold depths of interstellar space, silent wanderers in an ocean of darkness so profound that light itself becomes a distant memory. These are rogue planets, and they're far more common than anyone ever imagined. They drift through the Milky Way by the billions, perhaps trillions, each one a testament to the violent and chaotic process of planetary birth. Some were torn from their home systems in gravitational upheavals. Others never knew the warmth of a star at all. Born alone in the dark, they carry with them stories of cosmic catastrophe, of narrow escapes and eternal exile, of formation in the cold between the stars. Tonight, we'll explore how these mysterious worlds come to be, how we manage to find them when they emit no light of their own, and whether any of them, against all odds, might harbor life in their frozen depths. We'll discover planets that experienced growth spurts in the darkness, worlds that kept their moons during their exile, and the stunning revelation that there may be more of these orphaned worlds than there are stars to light the galaxy. And just before we begin this journey into the dark, if these calm explorations help you unwind or give you a peaceful way to end your day, I'd be grateful if you would consider liking this video and subscribing to the channel. It helps others who are seeking the same quiet comfort find their way here too. One sleepy soul at a time. Now, let the darkness embrace you, and let's drift together into the realm of worlds without suns, the art of finding the invisible. Imagine trying to find something that produces no light, reflects no starlight, and exists in the darkest regions of space imaginable. This is the challenge astronomers face when searching for rogue planets. Unlike the exoplanets that transit in front of their host stars, creating telltale dips in brightness we can measure, or the worlds whose gravity tugs on their stars in detectable ways, rogue planets offer almost nothing to see. They're phantoms, invisible wanderers drifting through an already dark cosmos. And yet, we've found them. Not just a handful, but hundreds confirmed, with strong evidence suggesting billions more await discovery. How do we accomplish this seemingly impossible feat? The answer lies in one of the universe's most elegant phenomena, a trick of gravity and light that Albert Einstein predicted over a century ago. The technique is called gravitational microlensing, and it works because mass bends space itself. When a massive object passes between us and a more distant star, its gravity acts like a lens, briefly magnifying the background star's light. For a few hours or days, that distant star grows brighter, then fades back to normal as the massive object continues its journey. By studying the exact pattern of that brightening, the duration, the shape of the light curve, astronomers can determine the mass of the object that passed in front. When that object is a planet with no nearby star, when the microlensing event shows no companion, no host, no gravitational anchor, we know we've glimpsed something remarkable, a world alone. The event is brief, never to repeat, a singular moment when a rogue planet's existence becomes known to us across vast distances. It's like catching a firefly's flash in an enormous, dark forest, a momentary spark that proves something moves through the shadows. The MOA telescope in New Zealand and the OGLE project in Chile have been watching millions of stars for these events. Patient observers waiting for the telltale brightening that signals a rogue planet's passage. In 2011, by analyzing microlensing data, astronomers found evidence for 10 Jupiter-mass objects with no associated stars nearby. From this sample, they estimated something extraordinary. There might be nearly 2 free-floating planets for every star in the Milky Way. Think about that for a moment. The galaxy contains hundreds of billions of stars, and there might be twice that many planets drifting alone between them. In 2020, astronomers announced an even more remarkable discovery through microlensing. They detected OGLE 22016 BLG 1928, a rogue planet with roughly the mass of Earth. For the first time, we had evidence of an Earth-sized world wandering the galaxy without a sun. Small, rocky, cold beyond measure, it drifts through interstellar space, a lonely twin to our own warm world. How it came to be there, whether it once knew the warmth of a star or formed in isolation, remains unknown. The microlensing event that revealed it lasted only briefly, and we'll never see it again. But we know it's out there, somewhere in the darkness. But microlensing isn't the only way we find these worlds. Young rogue planets, those still in the process of forming or recently formed, are slightly easier to detect. They retain heat from their formation, glowing faintly in infrared wavelengths. They're not hot enough to see in visible light, but sensitive infrared cameras can pick them out against the cosmic background. This is how, in 2021, a team of astronomers made one of the most significant discoveries in the study of rogue planets. Using data from multiple telescopes spanning 20 years, including the European Southern Observatory's Very Large Telescope in Chile and the European Space Agency's Gaia satellite, researchers identified at least 70 new rogue planets in a star-forming region near the Sun. The region, lying within the Upper Scorpius and Ophiuchus constellations, revealed these orphaned worlds like embers cooling in the dark. Each one had a mass comparable to Jupiter. Each one drifted alone, and each one represented a piece of the puzzle about how planetary systems form and sometimes fall apart. The team measured the motions, colors, and luminosities of tens of millions of sources across a large patch of sky. From this ocean of data, they identified the faintest objects, the ones not bright enough to be stars but still glowing with the residual heat of formation. These were rogue planets, some perhaps only a few million years old, still cooling from the violent processes that gave them birth. Nuria Miret Roeg, the lead astronomer on the project, expressed surprise at the findings. They didn't know how many to expect. They were excited to have found so many. The discovery nearly doubled the total number of known rogue planets and confirmed what theoretical models had been suggesting. These wandering worlds aren't rare cosmic oddities. They're abundant, perhaps representing a fundamental outcome of how planetary systems evolve. The actual number found falls into a range between 70 and 170 candidates, because determining whether something is truly a planet depends on its mass. Objects more than about 13 times Jupiter's mass are likely brown dwarfs, failed stars that never quite achieved the conditions for sustained nuclear fusion. But the team couldn't measure mass directly. They had to estimate based on brightness, which depends on age. Older objects have had more time to cool and grow dimmer. Younger objects shine brighter. Given the uncertainty about the exact age of the star-forming region they studied, the count remains somewhat uncertain, but even the conservative estimate represents a treasure trove of new worlds to study. And this is just the beginning. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, is expected to revolutionize our understanding of rogue planets. Unlike ground-based telescopes, Roman will have the stability and sensitivity to detect far more microlensing events. In its first 5 years of operation, it's projected to discover about 1,000 rogue planets. That number, as one researcher noted dryly, is probably a lower limit. The true number could be far higher. With each new discovery, with each technique refined and each telescope brought online, the invisible becomes visible. The dark spaces between the stars fill with worlds we never knew existed, a hidden population of planets that outnumber the stars themselves. Each one a world with its own story, its own journey through the eternal night, a galaxy teeming with orphans. Let's pause for a moment and truly absorb what we've learned. There might be billions of rogue planets in the Milky Way, possibly trillions. The estimates vary depending on the models and observations used, but even the most conservative calculations suggest an astonishing abundance. When you look up at the night sky and see the stars, brilliant points of light in the darkness, you're seeing only the luminous minority. Between those stars, in the vast gulfs of empty space, drift countless worlds in eternal darkness. In fact, rogue planets likely outnumber stars. Let that sink in as you drift towards sleep. For every sun, for every point of light you've ever seen twinkling overhead, there might be 2 or more planets wandering alone. Some estimates push that number even higher. One study suggested there could be up to 100,000 times more rogue planets than stars in the Milky Way, though this calculation included hypothetical objects much smaller than Jupiter, down to masses barely larger than moons. The sheer scale of this population changes how we think about planets themselves. We grew up with the idea that planets are things that orbit stars, that they're part of the solar systems, neat and ordered like beads on a string. But the universe doesn't work that way. Planets are, it seems, just as likely to wander alone as they are to circle a sun. Perhaps more likely, the rogue planets aren't the exception. In terms of pure numbers, they might be the norm, and worlds like Earth, snugly orbiting a stable star in a relatively calm system might be the outliers. This abundance tells us something profound about how planets form. The process is violent, chaotic, and messy. Young planetary systems are turbulent places where massive gas giants migrate inward, where worlds collide and gravitational battles rage. In this cosmic storm, many planets don't survive. They're flung out, cast into the darkness, their orbits stretched beyond breaking point until they escape their sun's gravity entirely. What we're seeing with rogue planets isn't a collection of rare accidents. It's evidence that planetary formation routinely produces casualties, worlds that lose the gravitational lottery and end up exiled. The 2017 discovery of Oumuamua, the first interstellar object observed passing through our solar system, reinforced this picture. Oumuamua appeared to be a comet or asteroid-like fragment born around another star, then cast out into interstellar space, a miniature version of a rogue planet. Its mere presence in our neighborhood implies that space is filled with these smaller, free-floating objects as well. Rogue planets, rogue asteroids, rogue comets, all of them fragments and survivors of planetary system formation across the galaxy, all of them wandering. And the numbers may actually be even larger when we account for smaller rogues. If Jupiter-mass planets can be ejected, then smaller, rocky planets like Earth or Mars should be ejected even more easily. They have less mass and less gravitational hold on their systems. During the violent reshuffling of young planetary systems, lighter worlds get tossed out more readily than heavy ones. The free-floating Jupiter-mass planets are actually the most difficult to eject, which means there might be even more free-floating Earth-mass planets wandering the galaxy. We just can't see them yet. They're too small, too dim, too cold. Imagine an Earth-sized world drifting through the darkness between stars. Its surface, if it ever had oceans, would be frozen solid, covered in nitrogen or oxygen ice depending on what atmosphere it once possessed. Any atmosphere thick enough might provide some insulation, but without a sun, temperatures would plunge to just tens of degrees above absolute zero. The sky would be black, not the black of night as we know it, but truly black, with only the faint, distant stars as pinpricks so dim they'd barely register. No moon would rise. No sun would ever warm the frozen landscape. This world would drift for billions of years, perhaps for the entire lifetime of the galaxy, never again feeling the embrace of starlight. Yet even in this profound isolation, the planet would not be entirely dead. Deep within its core, radioactive elements would continue to decay, generating heat. Residual warmth from its formation would seep slowly outward if the planet had a thick enough atmosphere or a substantial ice shell covering a buried ocean. That internal heat might maintain pockets of liquid water far beneath the surface. The world would be dark and cold on the outside, but in its hidden depths, conditions might exist for chemistry, for complexity, perhaps even for life. This is the paradox of rogue planets. They seem to represent absolute desolation, the ultimate isolation, and yet the sheer number of them and the diverse ways they can form and evolve means that some percentage, however small, might harbor environments where life could arise or persist. With trillions of rogue planets in the galaxy, even a tiny fraction hosting life would mean countless biological worlds drifting unseen through the dark. The statistics are humbling. If the Nancy Grace Roman Space Telescope finds 1,000 rogue planets in its first 5 years, and if each of those represents just the tip of a vast population we still can't fully detect, then the galaxy is more crowded with worlds than we ever imagined. Not crowded in the sense of being close together. The distances are still incomprehensibly vast, but crowded in the sense that planets, worlds, places that could tell stories of formation and evolution and possibly biology, fill the spaces we once thought empty. The Milky Way isn't just a collection of stars with their planetary systems arranged neatly around them. It's a galaxy where planets drift freely, where worlds wander, where the space between the stars is populated with orphaned spheres of rock and ice and gas, each one silently continuing its billion-year journey through the night. Exile and creation. The many ways to become a rogue. How does a planet end up alone? The story of a rogue planet's origin is often a story of violence, of gravitational chaos and narrow escapes, though not always. Some rogue planets never knew any other existence. They were born in the darkness and have lived there ever since. To understand these worlds, we need to understand both their births and their exiles. The most common path to becoming a rogue planet is ejection from a planetary system during its violent youth. Picture a young solar system, still forming, still settling. A massive protoplanetary disk of gas and dust swirls around a newborn star. Within that disk, worlds begin to coalesce. Small particles stick together, growing into pebbles, then boulders, then planetesimals, and finally into full-fledged planets. But this process isn't neat or orderly, especially when gas giants form. Gas giants like Jupiter and Saturn dominate the gravitational landscape of a planetary system. They're massive enough to significantly alter the orbits of everything around them. In many young systems, these giants migrate, moving inward or outward from where they formed, driven by interactions with the gas disk or with other planets. As they migrate, they can gravitationally scatter smaller worlds. A close encounter between a rocky planet and a gas giant can result in the smaller world being flung outward at tremendous speed, its orbit stretched into a long ellipse that eventually becomes a hyperbola, an escape trajectory. Once a planet's velocity exceeds its star's escape velocity, there's no coming back. The planet sails past the outer reaches of its former home and enters interstellar space. Within a few million years, it will be light years away, its star reduced to just another point of light in the sky, then eventually lost among countless others. The ejected planet might still be geologically active from its formation. It might still have an atmosphere. It might even have moons that survived the ejection, still orbiting their primary even as both drift away from the star forever. Planet-planet scattering is one mechanism, but it's not the only one, and studies suggest it can't fully explain the large number of free-floating planets we observe. There's something else going on, something more efficient at creating rogues. Binary star systems offer a particularly effective way to produce rogue planets. Many stars form in pairs, orbiting each other. Planets can form in orbits around one star of the binary, or in circumbinary orbits around both stars. These circumbinary planets face unique challenges. The gravitational influence of two stars creates complex dynamics, resonances, and instabilities. Research has shown that planets are naturally ejected from circumbinary systems at a higher rate than from single-star systems. The dance of the two stars, their mutual orbit, creates a shifting, gravitational landscape where planetary orbits can become unstable. When a planet in a circumbinary orbit gets perturbed, perhaps by interactions with other planets or by shifts in the binary stars themselves, it can be slingshot outward. Simulations of binary star systems and their planets show that ejections happen frequently, efficiently, and across a range of planetary masses. The binary acts like a gravitational catapult, and planets that get too close to the wrong resonance find themselves accelerated beyond escape velocity. This mechanism could account for a significant portion of the rogue planet population. Stellar flybys represent another avenue for creating rogues. Space isn't as empty as we often imagine, especially in star-forming regions where new suns are born in clusters. In these dense stellar nurseries, young stars with their nascent planetary systems can pass close to one another. If another star comes close enough to a planetary system, its gravity can disrupt the orbits of planets, particularly those in the outer regions. A close flyby might strip away planets entirely, sending them tumbling into the space between stars. Some of the rogue planets discovered in the Upper Scorpius region, for instance, might have been created this way. That region is a young stellar association, a place where stars formed relatively recently and still move in loose clusters. In such environments, stellar encounters happen more frequently than in the quieter regions of the galaxy. A planet that formed normally around its star could find itself suddenly homeless after a passing star's gravity wrenched it free. Then there are the most dramatic ejections, those caused by supernovae. When a massive star reaches the end of its life, it explodes in a cataclysmic supernova, blasting its outer layers into space and sometimes leaving behind a neutron star or black hole. Any planets orbiting that star face an unimaginable assault. The closest planets are destroyed outright, vaporized, or torn apart by the explosion. But planets farther out might survive, and the sudden loss of most of their star's mass means the star's gravitational hold weakens dramatically. Imagine being a planet orbiting a massive star. You've known nothing but the light and heat of your sun for millions or billions of years. Then, in an instant, that sun explodes. The shock wave rushes past you, battering your atmosphere if you have one, but you're far enough away to remain intact. But now your orbit no longer makes sense. You were in orbit around a star of, say, 20 solar masses. Now, suddenly, there's only a 1 or 2 solar mass neutron star remaining. You're moving too fast for this diminished mass to hold you. Your orbit stretches, becomes eccentric, and eventually becomes unbound. You sail away from the stellar remnant, away from the expanding supernova remnant, into the interstellar medium beyond. You're a rogue planet, created by the death of your sun. Research into supernova ejected planets has shown that they can retain their moons during this violent process. The sudden mass loss happens fast, but the gravitational binding between a planet and its moons is strong enough that they stay together. It creates a remarkable scenario where not just the planet, but an entire planet-moon system wanders into the dark, with tidal heating between the planet and its eccentric moons potentially creating environments where subsurface oceans could persist. But not all rogue planets have such dramatic origin stories. Some were never part of planetary systems at all. Some formed in isolation, directly from the collapse of gas clouds in space, much like how stars form, but without accumulating enough mass to ignite nuclear fusion. These objects blur the line between planets and brown dwarfs, failed stars. In star-forming regions, molecular clouds fragment into clumps of varying sizes. Most clumps that collapse become stars or brown dwarfs, but some clumps are small, just a few times Jupiter's mass worth of material. These can collapse under their own gravity, forming a planetary mass object without ever having a star to orbit. They're born alone, surrounded perhaps by their own small disk of leftover material, from which moons might form. Some of the young rogue planets detected in places like Upper Scorpius show evidence of having disks around them, just like young stars do. They have their own miniature protoplanetary disks, and astronomers have even observed active accretion, material falling onto these rogue planets from their disks. This strongly suggests they formed like stars, not like planets around stars. They're isolated planetary mass objects that represent the low-mass tail of the star formation process. One particularly remarkable example is CHA 1107-1626, a rogue planet located about 620 light-years away in the constellation Chamaeleon. This world has 5 to 10 times the mass of Jupiter and is surrounded by a disk of gas and dust. In 2024, astronomers using the European Southern Observatory's Very Large Telescope observed something astonishing. The planet experienced an enormous growth spurt, accreting material from its surrounding disk at a rate of 6 billion tons per second. That's the strongest accretion rate ever recorded for any planet, rogue or otherwise. The discovery revealed that the accretion wasn't steady. By August 2025, CHA 1107-7626 was accreting about 8 times faster than it had been just a few months earlier. The burst in activity appeared to be driven by magnetic fields, something only seen in stars before, not planets. Water vapor was detected during the accretion episode, present in the disk during the burst but not before. This rogue planet, drifting through space without a sun, was behaving like a young star, growing rapidly, surrounded by its own material, possibly forming a system of moons. Comparing archival data showed that the planet had experienced a similar growth burst in 2016, suggesting these episodes might be recurring part of the planet's normal formation process. Here was a world in the act of being born, alone in the dark, pulling in matter from the space around it, growing heavier and more complex. It blurred the distinction between planet and star, showing that formation mechanisms aren't always neat categories, but exist on a spectrum. So, rogue planets have diverse origins. Some are exiles, cast out from the warmth they once knew. Some are orphans of stellar death, surviving supernovae that destroyed their suns. Some are born alone, never knowing what it means to orbit a star. Each origin story shapes what kind of world the rogue planet becomes, what properties it has, whether it has moons, whether it retains an atmosphere, how much internal heat it possesses. The common thread is that all of them, regardless of how they came to be, now drift through the galaxy alone, traveling on trajectories that might never again bring them close to a star. Wanderers in a cosmos far more populated with orphaned worlds than any of us imagined. The journey through eternal night. What is it like to be a rogue planet? Not in any sentient sense, but what conditions define existence in the interstellar void? To understand these worlds, we have to confront the profound isolation and the physical extremes they endure, conditions so alien to our earthbound experience that they challenge imagination. First, there's the cold. Interstellar space is not entirely empty, but it's close. The average temperature of the universe, the cosmic microwave background radiation left over from the Big Bang, is about 2.7 degrees above absolute zero. That's minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. In the depths between stars, away from any source of warmth, temperatures hover near this cosmic baseline. For a rogue planet with no internal heat sources and no nearby star, the surface would cool until it reached equilibrium with the cosmic background. But most planets do have internal heat, at least initially. When a planet forms, whether by accretion in a disk or by gravitational collapse, the process generates tremendous heat. Material falling inward converts gravitational potential energy into thermal energy. Collisions between planetesimals heat things further. If the planet is massive enough, the core pressure alone generates heat. This primordial heat radiates slowly outward over millions and billions of years. A freshly formed or recently ejected rogue planet would start out warm and gradually cool. How quickly it cools depends on its size, composition, and whether it has an atmosphere. A large planet cools more slowly than a small one because it has more volume relative to its surface area. A rocky planet cools faster than a gas giant. A planet with a thick atmosphere cools much more slowly than one without, because the atmosphere acts as insulation, trapping heat and slowing its escape into space. Some theoretical models suggest that certain rogue planets could maintain relatively warm surface temperatures for billions of years. The key is a thick hydrogen atmosphere. Hydrogen, when compressed at high pressure, becomes opaque to infrared radiation. A planet with a massive hydrogen envelope would trap heat so efficiently that the greenhouse effect could keep surface temperatures well above freezing, even without a star. The pressure itself, the weight of the atmosphere pressing down, generates additional heat. For a time, possibly for the entire lifetime of the galaxy, such a world could have liquid water on its surface or in subsurface layers. More realistically, most rogue planets probably lose their atmospheres over time if they're not massive enough to hold them. Gas escapes into space, especially lighter elements like hydrogen and helium. A rocky rogue planet, Earth-sized or Mars-sized, would likely freeze solid within a few million years of ejection, its oceans turning to ice. its atmosphere condensing out onto the surface as frost or frozen gas. But beneath that ice, beneath the frozen surface, conditions might be different. Radioactive decay provides a long-lasting heat source. Earth's interior is kept warm partly by the decay of isotopes like uranium-238, thorium-232, and potassium-40. These elements have half-lives measured in billions of years, meaning they continue producing heat for timescales comparable to the age of the galaxy. A rogue planet with a substantial rocky mantle containing these elements would generate geothermal heat continuously, regardless of whether a sun warms its surface. If that heat is trapped beneath a thick layer of ice, it could maintain liquid water in a subsurface ocean. We see this in our own solar system. Jupiter's moon Europa has a surface of solid ice, but beneath that ice lies an ocean of liquid water, kept from freezing by tidal heating and possibly by radioactive decay in Europa's rocky core. Saturn's moon Enceladus has the same feature. Geysers of water erupting from its south pole prove the ocean's existence. These moons are far from the sun, receiving minimal solar warmth, yet they have liquid water because internal heat sources are sufficient. A rogue planet could be like Europa or Enceladus, but scaled up and completely unmoored from any star. Its surface would be a frozen wasteland, temperatures near absolute zero, but kilometers below that ice, in a dark ocean warmed by the planet's core, liquid water could persist for billions of years. And where there's liquid water and an energy source, there's a possibility for life. The sky above a rogue planet would be unlike anything we've experienced. Standing on the frozen surface, looking up, you'd see stars, but not in the way we see them from Earth. There'd be no atmosphere to scatter light, no moon to reflect the sun, no Milky Way glowing overhead. Just pure darkness punctuated by the faint points of distant stars, dimmer than you might expect because there's no star close enough to illuminate dust or provide context. You'd be adrift in a visual void, the stars too far away to offer warmth or light bright enough to read by, too distant to feel connected to anything. The silence would be absolute. No wind, because with temperatures so low, any atmosphere would have frozen out. No seismic activity on the surface, though deep below, the planet's interior might still churn slowly. Just stillness, a frozen moment stretched across geological timescales. If you could somehow survive there, stand on that ice and look around, you'd be witnessing one of the most isolated environments conceivable, a world truly alone. But isolation doesn't mean stasis. Rogue planets continue to evolve, just more slowly. Impacts from interstellar debris, though rare, would occasionally strike the surface. Cosmic rays would bombard the frozen crust, causing slow chemical changes in the ice. If the planet has a magnetic field, generated by its still molten core, that field would interact with the interstellar medium, the thin gas that fills the space between stars, creating faint auroras in whatever wispy atmosphere remains. And the planet moves. It's not stationary. It orbits the galactic center, just like stars do, following its own path through the Milky Way. Over millions of years, a rogue planet might travel through different regions of the galaxy, passing through spiral arms rich with gas and dust. crossing the quieter spaces between arms, occasionally even passing relatively close to other stars. Such close passes are rare. The galaxy is vast, but over billions of years, the probability increases. If a rogue planet passes close enough to a star, even if it doesn't get captured, the starlight could briefly warm its surface. For a few thousand years, the frozen world might experience a thaw, ice sublimating into gas, creating a temporary atmosphere. Then, as the planet continues on its trajectory and the star recedes into the distance, the cold returns, the atmosphere freezes, and the planet resumes its long night. These brief thaws might create short-lived opportunities for chemical complexity on the surface, fleeting moments of activity in an otherwise static existence. Some astrophysicists have even speculated that rogue planets could be temporarily captured by passing stars, entering orbit for a time before being ejected again. Simulations show that about 1% of all stars might experience such a temporary capture event. If a rogue planet enters orbit around a star, even for just a few million years, it receives warmth and light. Frozen oceans melt. Atmospheres thicken. The planet might resemble a normal world for a time before another gravitational encounter flings it back into the darkness. It's a rare scenario, but with trillions of rogue planets and billions of stars, these events happen somewhere in the galaxy all the time. The journey of a rogue planet is one of almost unimaginable duration. These worlds will drift through space for as long as the galaxy exists, tens of billions of years or more, until the stars themselves begin to die out and the universe grows cold and dark. In a sense, rogue planets are living previews of the galaxy's far future, when star formation has ceased, when all suns have exhausted their fuel, and darkness reclaims the cosmos. They're worlds out of time, experiencing in the present what all worlds will eventually face in the deep future, an eternity of cold and silence. Yet even in that cold, there's a kind of peace. No violent stellar flares to scour the surface. No asteroid bombardments as intense as those in busy planetary systems. No gradual approach of an aging, swelling sun that will eventually consume inner worlds. A rogue planet is free from these fates. It simply exists, drifting, cooling slowly, carrying within it whatever story it began with, whether that's the memory of a lost sun, the signature of formation in a stellar nursery, or the quiet heat of radioactive decay keeping hidden oceans warm. In the grand cosmic scale, these planets are whispers in the dark, nearly invisible, rarely noticed, but far more numerous than the bright, obvious worlds orbiting stars. And some of them, perhaps, hold secrets that challenge our understanding of where life can arise and persist. Life in the dark, the astonishing possibility. Could a world without a sun host life? The question seems almost absurd at first. Life as we know it depends on energy, and we're accustomed to thinking of stars as the primary energy source for biological systems. Plants photosynthesize sunlight, feeding themselves and producing oxygen. Herbivores eat plants. Carnivores eat herbivores. The entire food chain on Earth's surface ultimately traces back to the sun's energy. But that's not the complete picture, even on Earth. Deep beneath the ocean surface, far beyond the reach of sunlight, life thrives around hydrothermal vents. These vents, often called black smokers, are cracks in the ocean floor where superheated water, rich in dissolved minerals, pours out into the cold ocean. Bacteria at these vents don't use photosynthesis. They use chemosynthesis, extracting energy from chemical reactions involving hydrogen sulfide, methane, and other compounds. These bacteria form the base of a food web that includes tube worms, clams, crabs, and fish, entire ecosystems completely independent of the sun. This proves that life doesn't require sunlight, only energy and the right chemical ingredients. If chemosynthesis works on Earth, it could work on a rogue planet, provided there's a source of chemical energy in liquid water where reactions can occur. Let's consider what a habitable rogue planet might look like. Picture a rocky world, perhaps the size of Earth or slightly larger, ejected from its planetary system a few billion years ago. It's had time to cool, its surface frozen solid, covered in a kilometers-thick layer of ice. But beneath that ice lies an ocean, kept liquid by geothermal heat from the planet's core. That heat comes from radioactive decay, the breakdown of long-lived isotopes scattered through the planet's mantle. At the bottom of this dark ocean, where it meets the rocky core, hydrothermal vents release hot, mineral-rich water. The temperature difference between the vent water and the surrounding ocean creates chemical gradients, thermodynamic disequilibrium that life could exploit. Microbes might evolve to use these gradients, harvesting energy from the reactions between hot vent fluids and cold ocean water, just like microbes do at Earth's black smokers. These microbes wouldn't photosynthesize. They'd never see light, never produce oxygen, never create anything like the lush biosphere of Earth's surface. But they'd be alive, metabolizing, reproducing, evolving. Over time, they might diversify, some specializing in different chemical reactions, others feeding on the first group, creating a simple ecosystem. Complexity could grow slowly on a timescale of billions of years. In 2021, researchers introduced the concept of urability, distinct from habitability. Habitability refers to conditions that can sustain life, that allow existing life to persist. Urability refers to conditions that can give rise to life in the first place, that enable abiogenesis, the origin of life from non-living chemistry. A rogue planet with subsurface oceans might be both habitable and urable. The energy from hydrothermal vents, the chemical diversity, the presence of liquid water, and the long timescales all create conditions where life might not just survive if it were introduced, but actually originate. Of course, there are challenges. Life needs more than just water and energy. It needs the right elements, complex organic molecules, phosphorus, nitrogen, sulfur, trace metals. A rogue planet would have inherited these from its formation, from the molecular cloud or protoplanetary disk where it coalesced. If those materials are present, if they're available in the subsurface ocean, then the ingredients for life are there. The question becomes one of probability. With trillions of rogue planets in the galaxy, even if only a tiny fraction have the right combination of size, composition, internal heat, and liquid water, that still leaves countless worlds where life could potentially arise. Some researchers have even speculated that rogue planets might contain most of the biomass in the Milky Way. This sounds exciting, but consider the logic. If there are more rogue planets than there are regular planets orbiting stars, and if even a small percentage of rogue planets develop subsurface life, then the total number of living microbes on rogue planets could exceed the total on all sunlit worlds combined. Life on Earth is abundant partly because of photosynthesis, which is incredibly energy efficient. But chemosynthetic life can also be productive if nutrients and energy are available rogue planet. Biospheres might be slow, cold, and dark, but across trillions of worlds and billions of years, they could add up to a significant fraction of the galaxy's living matter. There's another intriguing possibility involving rogue planets and life: the concept of panspermia. Panspermia is the idea that life can be transferred between worlds, that microbes or organic molecules from one planet might travel through space and seed life on another. Traditionally, panspermia scenarios imagine rocks blasted off a planet by an impact, carrying microbes into space, drifting for millions of years, then landing on another world and establishing a biosphere there. Rogue planets could act as vehicles for panspermia on an interstellar scale. Imagine a rogue planet with subsurface life passing near a star system with habitable planets. If the rogue planet's trajectory brings it close enough, gravitational interactions could strip away part of its icy shell, sending chunks of ice containing dormant microbes into space. Some of those chunks might enter orbit around planets in the star system. If they land on a world with suitable conditions, the microbes could awaken, thaw, and begin multiplying. The rogue planet would have delivered life from one corner of the galaxy to another, a wandering seed ship spreading biology through the cosmos. This scenario is highly speculative and requires many unlikely conditions to align. The rogue planet has to pass close to a planetary system, something rare given the vastness of space. The ejected material has to land on a habitable world. The microbes have to survive the journey, which could last millions of years in the freezing vacuum of space. And the receiving world has to be hospitable. But with trillions of rogue planets wandering the galaxy over billions of years, even very low probability events will happen many times. Some scientists, including prominent astrophysicist Avi Loeb, have suggested that based on the population of interstellar objects discovered in the solar system, more rocky material might have been ejected from planetary systems than exists in those systems. If rogue planets outnumber bound planets, and if some of them carry life, then perhaps life itself is more common in the isolated darkness than in the light of stars. It's a thought that inverts our assumptions about where biology flourishes. There's even the possibility, though extremely remote, that life on Earth was delivered by a rogue planet in the distant past. Early in the solar system's history, when the inner planets were still forming and being bombarded by debris, a passing rogue planet might have had a close encounter, shedding material that eventually made its way to Earth. If that material carried microbes or complex organic molecules, it could have jump-started or influenced the origin of life on our world. We have no direct evidence for this, and it remains purely speculative, but it illustrates how rogue planets could, in principle, connect the biospheres of otherwise isolated star systems. And then there are rogue planets near the galactic core. If a rogue planet orbits close enough to an active galactic nucleus, the supermassive black hole at the galaxy's center that's actively feeding and emitting intense radiation, then it might receive enough light for photosynthesis. Manas V. Lingam, a researcher in astrobiology, has calculated that there's enough energy to support photosynthesis within about 1,000 light-years of an active galactic nucleus. A rogue planet in that region, if it has an atmosphere and surface water, could develop photosynthetic life despite not orbiting a star. It would be an extraordinary environment, bathed in the radiation from the galactic core, a lonely world with green continents lit by the glow of a distant supermassive black hole. These scenarios push the boundaries of our understanding and venture deep into speculation. We have no confirmed examples yet of life on rogue planets. We can barely detect the planets themselves, let alone analyze their compositions or search for biosignatures. But the theoretical foundations are sound. Life needs water, energy, and the right chemicals. Some rogue planets have water. Some have energy sources like geothermal heat. And all planets inherit chemicals from their formation. The pieces are there. Whether they've assembled into living systems on any of the countless rogue planets drifting through the Milky Way remains one of the great open questions of astrobiology. As you drift towards sleep, consider this. Somewhere in the darkness between the stars, on a world that has never seen a sun, there might be an ocean. In that ocean, heated by the slow decay of atoms in the planet's core, there might be vents releasing minerals into the water. Near those vents, microscopic life might be metabolizing, growing, dividing, adapting, creating a biosphere in the eternal dark. We may never find it. We may never know it exists. But the universe is vast, and the number of rogue planets is staggering. The silence of the dark, it seems, might not be as empty as we think the moons that followed. Companions in exile. A rogue planet's exile need not be solitary. Some of these wandering worlds did not leave their home systems alone. They brought companions, moons that stayed gravitationally bound through the violence of ejection, continuing to orbit their primary even as both sailed into interstellar darkness. These rogue moons add another layer of complexity to the story of life in the void, because moons offer something planets might not: tidal heating. When a planet is ejected from its system, the process is chaotic. Gravitational perturbations, close encounters with other massive bodies, rapid acceleration to escape velocity. All of these could disrupt the delicate orbits of moons. You might expect moons to be stripped away, left behind as the planet flees, or flung off into their own independent trajectories. But research has shown that in many cases, moons survive. Studies of planet-planet scattering events, where one world flings another out of the system, indicate that moons orbiting the ejected planet typically remain bound. The moon's orbit around its planet is determined by their mutual gravitational pull, and as long as the ejection happens relatively quickly compared to the moon's orbital period, the moon doesn't have time to be pulled away by external forces. It stays locked in orbit, and both planet and moon enter interstellar space together. The same is true for ejections caused by supernovae. When a massive star explodes, and the sudden loss of stellar mass unbinds planets from their orbits. Simulations show that planet-moon systems can remain intact. The gravitational bond between the planet and its moon is strong enough to survive the transition. In fact, a detailed study published in 2025 examined scenarios where planets are ejected by Type II supernovae and found that moons not only remain bound but often have their orbits reshaped into eccentric ellipses by the violence of the ejection. And this is where things get interesting. An eccentric orbit, one that's elongated rather than circular, creates tidal forces between the moon and the planet. As the moon moves closer to the planet during its orbit, tides on both bodies grow stronger. As it moves farther away, tides weaken. This constant flexing generates heat, the same process that keeps Europa's subsurface ocean liquid, despite the moon's distance from the sun. In the case of a rogue planet-moon system, tidal heating could provide a long-lasting heat source independent of radioactive decay or residual formation heat. The study mentioned earlier ran thousands of simulations, modeling rogue planet-moon systems created by supernova ejections. The results were striking. In a significant minority of configurations, tidal heating was strong enough to maintain subsurface liquid water on the moons for billions of years. These moons wouldn't rely solely on the planet's geothermal heat. They'd generate their own heat through tidal flexing, potentially creating more dynamic and energy-rich environments than a static, frozen world could provide. Imagine a moon orbiting a rogue gas giant, something like a super Jupiter, adrift between the stars. The moon is rocky, perhaps Earth-sized or smaller, and its surface is frozen. But its orbit is eccentric, thanks to the violence of its ejection. Every few days or weeks it swings close to the gas giant, and the enormous tidal forces stretch and squeeze the moon's interior. Rock grinds against rock. Heat builds up. That heat melts ice deep beneath the surface, creating an ocean. In the ocean, near the moon's core, hydrothermal vents release minerals. And in those vents, chemistry happens, complexity grows, and perhaps, eventually, life arises. This moon would be orbiting a planet that itself orbits nothing. The sky would show the massive bulk of the gas giant, enormous and dark, illuminated only by faint starlight, or by whatever dim infrared glow the planet still emits. The moon would experience eclipses as it passes into the planet's shadow, though there'd be no sun to cast that shadow in the traditional sense, just a blocking of the already faint light from distant stars. It would be an alien sky, dominated by a vast, dark world hanging overhead, a companion in eternal exile. The potential population of these rogue moons is staggering, if theories suggesting 2 rogue planets for every star are correct, and if even a fraction of those planets have moons, then there could be trillions of rogue moons in the Milky Way. Some might be captured objects, moons that were themselves once independent bodies before being gravitationally bound to a planet. Others might have formed in orbit around the planet when both were still part of a solar system. Regardless of origin, they represent yet another category of worlds, moons without suns. orbiting planets without suns, drifting through the galaxy in pairs or small families. Detecting these moons is currently beyond our capabilities, but that might change soon. The Nancy Grace Roman Space Telescope, with its sensitivity to microlensing events, could potentially detect rogue moons if conditions align just right. When a rogue planet passes in front of a background star and causes a microlensing event, a moon orbiting that planet could create a secondary brightening, a subtle additional signature in the light curve. Teasing out these moon signals from the data will be challenging, but not impossible. Within the next decade or two, we might confirm the first rogue moon, proving that these companion worlds exist, and they might be more hospitable to life than their host planets. A large rogue planet, a gas giant, can't support life directly. It has no solid surface, just crushing atmospheric pressures and storms. But its moon, a rocky world with subsurface oceans warmed by tidal heating, could be a thriving biosphere. The irony is that the moon's habitability depends on the planet's presence. Without the planet's gravity to generate tides, the moon would be just another frozen rock. With the planet, the moon becomes a potential cradle for life. Research into rogue moons has also revealed that the tidal heating can persist for billions of years, potentially for the entire lifetime of the galaxy. The eccentricity of the moon's orbit, the constant flexing and heating, doesn't dampen quickly. Over time, the orbit might circularize, reducing tidal forces, but the timescales for this are so long that life would have ample time to originate, evolve, and perhaps even develop complexity. There's a beautiful symmetry here. In our own solar system, we suspect that some of the most promising places to search for life are moons like Europa, Enceladus, and Titan, worlds that orbit gas giants far from the Sun. We think life might exist in Europa's ocean, warmed by tidal heating from Jupiter's gravity. Now, we realize that the same scenario could play out on rogue moons, except without any star at all. Life doesn't need the Sun if it has a gas giant to orbit, if it has tidal heating and subsurface oceans and chemical energy. The idea that moons of rogue planets could support life challenges our definition of habitable environments. We're used to thinking about habitable zones around stars, regions where temperatures allow liquid water on a planet's surface. But rogue moons introduce habitable zones around planets, regions where tidal heating and atmospheric insulation create conditions for subsurface oceans. The galaxy's habitable real estate might extend far beyond what we've imagined, into the dark spaces where no star shines but where gravity and heat conspire to create pockets of warmth. And there's another intriguing consideration. If rogue moons can develop life, they might also serve as panspermia vectors, just like their host planets. A rogue planet-moon system passing near a star system could have material stripped from the moon's surface, perhaps by tidal forces from the star's gravity, or by impacts from debris in the star system. That material, carrying microbes from the moon's ocean, could be deposited on planets orbiting the star, seeding them with life that originated in the interstellar void. Biology from the darkness arriving in the light, a transfer of life from worlds without suns to worlds with them. As you close your eyes and let sleep approach, picture this. a moon orbiting a dark gas giant, both adrift between the stars. The surface is ice, but beneath, heated by the endless tidal dance, an ocean swirls. In that ocean, near vents in the rocky core, tiny organisms metabolize and reproduce, oblivious to the fact that they exist in one of the loneliest places in the galaxy, a moon without a sun, orbiting a planet without a sun, both wandering through the night. And yet, they live. They persist. They adapt. Life finds a way, even in the dark. The most remarkable discoveries. Among the hundreds of rogue planets we've detected, a few stand out for their extraordinary properties, worlds that challenge our expectations and reveal how diverse and dynamic these objects can be. Let's explore some of the most remarkable rogue planets discovered so far. Each one a story of cosmic violence, isolation, and the strange physics of world-building in the dark. First, there's CHA 1107-7626, the rogue planet we mentioned earlier. Located about 620 light-years away in the constellation Chamaeleon, this world is 5 to 10 times the mass of Jupiter. But what makes it extraordinary is not its size, but its activity. Using the James Webb Space Telescope in 2024, astronomers made a clear detection of a disk of gas and dust surrounding the planet, a protoplanetary disk similar to those around young stars. This disk is feeding the planet, and the planet is growing, and observations made with the European Southern Observatory's Very Large Telescope. Researchers discovered that CHA 1107-7626 was accreting material at a rate of 6 billion tons per second. That's not a typo. 6 billion tons every second. This is the strongest growth rate ever recorded for any planetary mass object, rogue or otherwise. The planet experienced a massive growth spurt, its accretion increasing by a factor of 8 over just a few months. What's driving this furious feeding frenzy? The answer appears to be magnetic fields. By comparing the light emitted before and during the burst, astronomers gathered clues about the accretion process. Magnetic activity, something typically seen in stars but not in planets, played a significant role in driving the dramatic infall of mass. The magnetic field channels material from the disk onto the planet, funneling gas and dust along field lines toward the poles, accelerating it to high speeds before it crashes onto the surface. This discovery blurred the line between planets and stars. CHA 1107-7626 behaves more like a young T-Tauri star, actively accreting from a disk magnetically active, growing rapidly, than like a traditional planet. And yet, it's not massive enough to ever ignite hydrogen fusion. It's a rogue planet, born in isolation or ejected early in its life, surrounded by its own material, possibly in the process of forming moons. The disk around CHA 1107-626 contains water vapor detected during the accretion episode, but not before. The chemistry of the disk changed as the planet fed, revealing complex processes at work. Observations also showed that the planet had experienced a similar growth burst in 2016, suggesting these episodes are recurring, part of the planet's long-term evolution. Over millions of years, CHA 1107-7626 might continue to accrete material, growing heavier and perhaps forming a system of satellites before the disk finally dissipates. Then there's Ogle 2016 BLG 1908, the first Earth mass rogue planet detected. Discovered through gravitational microlensing in 2020, this world is roughly the same mass as our own planet, but it orbits no star. The microlensing event that revealed it was incredibly brief, the shortest ever recorded for a free-floating planet, lasting only a few hours. From that fleeting brightening of a background star, astronomers calculated the mass and determined that no star was nearby. Ogle 2016 BLG 1928 is significant because it proves that small, rocky rogue planets exist, not just gas giants. We've known theoretically that Earth-sized worlds should be ejected from planetary systems, possibly even more frequently than larger planets. But detecting them is extraordinarily difficult. They're tiny, cold, and dark. The fact that we found one at all suggests there are countless others out there, too faint for current technology to detect. When the Nancy Grace Roman Space Telescope begins operations, it's expected to find many more of these small rogues, giving us a better sense of how common Earth-like worlds are in the interstellar void. Imagine a planet like Earth, with continents and ocean basins, perhaps once with an atmosphere and life, ejected from its solar system and sent tumbling into the darkness. Its oceans would freeze. Its atmosphere would condense. Any life on the surface would perish within days or weeks. But if it had subsurface biomes, microbial life deep underground or in caves, those organisms might survive, sustained by geothermal heat, continuing to live in the dark as their world drifted away from everything it once knew. Ogle 2016 BLG 1928 might be such a world, a frozen Earth analog carrying within it a preserved biosphere from a time when it orbited a star. Among the young rogue planets discovered in Upper Scorpius, several have shown evidence of disks, like CHA 1107 7626. OTS 44 is another example. Observations with the Herschel Space Observatory and the Very Large Telescope revealed that this young rogue planet, only a few million years old, is surrounded by a disk of at least 10 Earth masses worth of material. The disk is actively accreting, similar to disks around young stars, and spectroscopic data showed that the accretion process closely resembles what happens in canonical star formation. This supports the idea that at least some rogue planets form like stars, through direct collapse of gas clouds, rather than through ejection from planetary systems. OTS-44 could eventually form a large satellite system, moons orbiting it, all of them wandering together through the galaxy. It's a miniature solar system in the making, but one that will never have a sun at its center, only this planetary mass object and whatever companions coalesce from its disk. Then there are the binary rogue planets, two planetary mass objects orbiting each other, untethered to any star. The first resolved planetary mass binary was 2, mass J1191137AB, two worlds locked in mutual orbit, drifting together. Several others have been discovered since, including systems where the two objects might be roughly equal in mass, true binary companions rather than a planet and a much smaller moon. These binaries pose interesting questions about formation. Did they form together from the same collapsing cloud, like binary stars? Were they planets in a system that got ejected as a pair? Or did they meet by chance in interstellar space and capture each other gravitationally? Each scenario is possible, and likely different binaries have different origins. But their existence shows that rogue planets don't all wander alone. Some have partners, companions in exile, orbiting each other as they drift through the dark. There's also speculation about even more exotic objects. Hypervelocity rogue planets ejected from the galactic center by interactions with the supermassive black hole could be traveling at tremendous speeds, possibly even approaching a significant fraction of the speed of light. Avi Loeb and colleagues have modeled scenarios where interactions between the Milky Way's central black hole and incoming black holes, such as during the future merger with Andromeda, could fling stars and planets outward at relativistic speeds. A rogue planet traveling near the speed of light would be a bizarre object, time-dilated, experiencing the galaxy's evolution in fast forward, though from an external observer's perspective it would just be a faint, rapidly moving speck. These hypervelocity rogues might escape the Milky Way entirely, entering intergalactic space, joining a hypothetical population of truly unbound planets wandering the voids between galaxies. We have no direct evidence for such objects yet, but the mechanisms for their creation are plausible, and the galaxy has been around long enough for rare events to have happened many times. Every discovery of a new rogue planet, every observation of their properties, refines our understanding. We're learning that these worlds are not all frozen, dead balls of rock or gas. Some are active, accreting, growing. Some have disks and may form moons. Some are small and rocky, others are massive gas giants. Some wander alone, others in pairs. The diversity is astonishing, reflecting the many pathways through which planets can come into existence and the many fates they can suffer. As you rest, as your thoughts slow and sleep approaches, let these strange worlds drift through your mind. A planet growing in the dark, pulling in gas at billions of tons per second. An Earth-mass world frozen solid, tumbling through space with no sun to light its way. Binary planets orbiting each other, companions forever. Hypervelocity rogues racing at nearly the speed of light. Each one is real. Each one is out there, somewhere in the vast Milky Way, continuing its journey. The future, what awaits discovery. We've found hundreds of rogue planets. We've begun to understand their origins and their properties. But we're only scratching the surface. The coming decades promise to revolutionize our knowledge of these wandering worlds, as new telescopes and new techniques bring thousands more into view and allow us to study them in unprecedented detail. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, is poised to become the premier rogue planet hunter. Roman is designed specifically for wide-field surveys and will conduct extensive microlensing campaigns, monitoring millions of stars simultaneously for the brief brightening events that signal a passing rogue planet. Its sensitivity far exceeds that of ground-based surveys, allowing it to detect smaller, less massive planets. In its first 5 years of operation, Roman is expected to discover roughly 1,000 rogue planets, and that's a conservative estimate. The true number could be far higher. What makes Roman particularly powerful is its ability to characterize these planets, not just detect them. By measuring the duration and shape of microlensing events with high precision, astronomers can determine not only the mass of the rogue planet, but also clues about its composition, whether it's rocky or gaseous, and potentially even whether it has an atmosphere or moons. A moon orbiting a rogue planet would create a subtle secondary signal in the microlensing curve, a small deviation that Roman's instruments might catch. If successful, this would mark the first confirmed detection of a rogue moon. Roman will also help answer fundamental questions about the rogue planet population. How common are Earth mass rogues compared to Jupiter mass ones? Are rogue planets uniformly distributed throughout the galaxy, or do they cluster in certain regions? What's the ratio of rogues that formed in isolation versus those ejected from planetary systems? These questions require large statistical samples, and Roman will provide them. Beyond Roman, the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will contribute to rogue planet science through its wide-field surveys. Rubin will repeatedly image the entire visible sky, creating a time-lapse of the heavens. While it's primarily designed to detect moving objects like asteroids and track transient events like supernovae, it could also catch rare instances of young rogue planets moving through star-forming regions, or detect microlensing events in coordination with other telescopes. Rubin's data will complement Roman's, providing a different perspective on the rogue planet population. The James Webb Space Telescope, already operational, is uniquely suited to study young rogue planets through direct imaging. Its infrared sensitivity allows it to detect the faint glow of planets still warm from formation, even those unbound to stars. Webb's spectrographs can analyze the light from these objects, revealing details about their atmospheres, temperatures, and chemical compositions. The discovery of water vapor in the disk around CHA 1107-626 was made with Webb, and similar studies of other rogue planets will follow, building a picture of what these worlds are like shortly after birth. The upcoming Extremely Large Telescope, under construction in Chile and due to begin observations in the early 2030s, will take direct imaging to the next level. With a mirror 39 meters in diameter, the ELT will be the most powerful optical telescope ever built. It will be able to study young rogue planets in exquisite detail, resolving their disks, detecting companions, and possibly even imaging large moons. The ELT might catch rogue planets during their accretion bursts, like the ones observed on CHA 1107-7626, providing real-time data on how these objects grow and evolve. There are also proposals for future space missions specifically designed to study rogue planets and interstellar objects. A mission equipped with a fast response system could, in theory, visit a rogue planet passing through the outer solar system, conducting a flyby and collecting data up close. This would require detecting the object early enough to plan and launch an intercept. A challenging, but not impossible task. The discovery of MUA in 2017 showed that interstellar objects do pass through our neighborhood, and rogue planets, being more massive and slower moving than small comets, might be easier targets for such a mission. As our catalog of rogue planets grows, patterns will emerge. We'll learn which formation mechanisms are most common, which types of stars are most likely to produce rogues through ejection, and how the rogue population compares across different regions of the galaxy. We'll identify clusters of rogues in young star-forming regions, and we'll track their kinematics, how fast they're moving and in what directions, to trace their origins back to specific stellar nurseries or planetary systems. Perhaps most excitingly, we'll begin to assess the habitability potential of rogue planet and their moons. If we can detect atmospheres on rogue planets, analyze their compositions, and identify worlds with subsurface oceans, we'll have targets for future astrobiology missions. Searching for biosignatures on a rogue planet is far more challenging than on a planet orbiting a star. You can't use transit spectroscopy because there's no star to transit, but other techniques might work. If a rogue planet has a thick atmosphere and internal heat, it might emit detectable levels of gases like methane or phosphine, which on Earth are associated with biological processes. A spectrograph sensitive enough to analyze the faint thermal emission from a rogue planet could, in principle, search for such gases. We might also discover rogue planets in unusual locations. Planets near the galactic center, warmed by the radiation from the central black hole's accretion disk, could be detectable as anomalous heat sources. Rogue planets in the galactic halo, far from the disk's star-forming regions, could reveal information about the early history of the Milky Way, as they might have been ejected billions of years ago during the galaxy's youth. Each discovery adds a piece to the puzzle of galactic evolution. And there's always the possibility of surprises. We've been surprised by almost every aspect of rogue planets so far: their abundance, their diversity, the fact that some are still actively forming. Future observations will undoubtedly reveal phenomena we haven't predicted. Types of rogue planets or rogue moons that don't fit into our current categories, or behaviors that challenge our models. Science is at its best when it encounters the unexpected, and the study of rogue planets is still young enough that many surprises likely await. In the coming decades, rogue planets will transition from being mysterious, poorly understood objects on the edge of astronomy to being a well-studied class of worlds with their own dedicated field of research. Conferences will focus on them. Textbooks will have chapters on their formation, evolution, and potential for habitability. Children learning about planets will grow up knowing that not all planets orbit stars, that the galaxy is full of wandering worlds, and that darkness isn't the absence of possibility, only the absence of light. As you drift toward sleep, imagine the future astronomers will create. Detailed maps of thousands of rogue planets, their masses, trajectories, and properties cataloged. Spectra revealing atmospheres, detecting water, methane, maybe even hints of biological activity. Images of rogue planet-moon systems, companions in exile. And perhaps, someday, a mission to visit one, a spacecraft that travels to a rogue planet in the outer reaches of the solar system's neighborhood, sending back images of a world that has wandered the galaxy for eons, finally, seen up close by curious minds from a world that still knows the warmth of a sun. wanderers in the cosmic night. We've journeyed together through the story of rogue planets, these orphaned worlds drifting through the darkness between the stars. We've learned how they're born, both in exile and in isolation. We've explored how astronomers find them, despite their invisibility. We've confronted their staggering numbers, billions or trillions populating the Milky Way, outnumbering the stars themselves. We've considered their journeys through the eternal night, frozen surfaces concealing hidden oceans warmed by geothermal heat. We've speculated about life in the dark, chemosynthetic biospheres thriving without sunlight, and about rogue moons heated by tidal forces, potential cradles for biology. We've met remarkable individuals, Cha 1107 72626 growing at an astounding rate, OGL 22016 LG 1928 the Earth Mass Wanderer, and binary systems where two planets orbit each other in exile. We've looked ahead to the discoveries waiting in the coming years, the thousands of rogue planets that the Nancy Grace Roman Space Telescope will reveal, the detailed studies that Webb and the extremely large telescope will conduct, and the possibility of missions to visit these worlds. Throughout all of this, a theme has emerged. Rogue planets challenge our understanding of what it means to be a planet. They show us that worlds don't need suns to exist, that planets are as much a part of the galaxy's structure as stars are, and that the universe is far more populated with worlds than the number of bright points in the night sky would suggest. They remind us that isolation doesn't mean stillness, that even in the darkest corners of space processes unfold, chemistry happens, and perhaps life finds a way. There's something profoundly poetic about rogue planets. They're wanderers, exiles, orphans. They've lost their homes, if they ever had them, and now they drift through a cosmos that seems indifferent to their existence. And yet, they endure. They carry within them heat from their origins, echoes of the violence or the quiet collapse that gave them birth. Some of them might harbor life, microbes in hidden oceans that have never seen light and never will. Those organisms, if they exist, would know nothing of stars, nothing of day or night as we understand it, only the slow rhythm of their world's geothermal pulses and the chemistry of their dark water. In a way, rogue planets are living testaments to the galaxy's deep time. They've been drifting for billions of years, and they'll continue for billions more. When our sun expands into a red giant and consumes the inner planets, when the Milky Way and Andromeda collide and merge into a new galaxy, when the universe grows so old that the star formation ceases and the last stars burn out, the rogue planets will still be there, frozen monuments to an age when stars shone and warmth was possible. But they're also testaments to resilience. Despite being cast out, despite losing the light and warmth of their suns, they persist. They carry their stories with them, encoded in their compositions, their motions, their moons. And perhaps, just perhaps, they carry life, biology that originated in darkness, that knows no other way to exist, thriving quietly as it has for eons. We'll never meet most of them. The galaxy is too vast, and they're too faint. But knowing they're out there changes something. It expands the boundaries of where we think life can exist. It humbles us, showing that Earth's place in the cosmos, orbiting a stable star in a relatively calm system, is not the default but a stroke of cosmic fortune. And it fills the dark spaces of the galaxy with meaning. The voids between stars aren't empty. They're full of worlds, each one a story, each one a mystery. As you close your eyes tonight, as sleep finally takes hold, let your mind drift among these wandering worlds. Picture a planet far from any star, its surface frozen, its sky black. Picture an ocean beneath kilometers of ice, warmed by the planet's core. Picture hydrothermal vents on the ocean floor, and microbes clustered around them, living, adapting, unaware that they exist in one of the loneliest places imaginable. Picture a moon orbiting that planet, heated by tidal forces, its own ocean swirling with life. Picture binary planets, two worlds orbiting each other, companions in eternal exile. Picture young rogue planets still surrounded by disks, growing, pulling in gas and dust, forming moons. Picture an Earth mass rogue tumbling through space, a frozen twin to our own world. Picture hypervelocity rogues racing through the galaxy at nearly the speed of light, time dilated, fleeing toward intergalactic space. And picture yourself, here on our Earth, orbiting a sun, part of a solar system, surrounded by warmth and light. You're one of the lucky ones, living on a world that stayed, that wasn't exiled, that knows the rhythm of sunrise and sunset. But you share the galaxy with countless other worlds, most of them wandering in darkness. And that connection, the kinship between all worlds regardless of whether they circle stars, is part of what makes the universe so beautiful. Thank you for drifting through the cosmos with me tonight. Thank you for exploring these quiet mysteries, for letting your mind wander among worlds that wander. If this journey helped you unwind, if it gave you a peaceful way to end your day, I'd be grateful if you'd consider liking this video and subscribing to Sleepy Science Society. It helps others who are seeking the same calm find their way here. The rogue planets continue their journeys, drifting through the Milky Way, through time, through the darkness. Some will wander for the lifetime of the galaxy. Some might one day by chance pass close to a star and feel warmth again. However briefly, most will simply drift, patient and silent, carrying whatever secrets they hold deep within. And you, as you rest, as you breathe slowly and let the weight of the day lift away, you're part of this same cosmos, made of atoms forged in stars, living on a world that orbits one, but connected through the vastness of space to all the other worlds, even those that wander alone. Sleep well and dream softly. The universe is vast and full of mysteries, but tonight you've explored one of them, and tomorrow there will be more waiting. Good night.